Welcome. In this video, I'm going to give a brief conceptual overview of analysis of covariance. So analysis of covariance is an analysis that sort of bridges the gap between ANOVA, where we're looking at mean differences in an interval ratio dependent variable across levels of one or more categorical independent variables, and regression, where we typically have a interval ratio predictor or sets of interval ratio predictors attempting to predict values of an interval ratio outcome variable. In ANCOVA, on the explanatory variable side, the predictors, we have one or more independent variables, which are categorical and are usually the focal variables for the hypothesis, but we also have a covariate, which is in most ANOVA and ANCOVA analyses, the covariate is a statistical control variable that's an interval ratio variable that we're attempting to statistically control for to see what is the relationship between the IVs and potentially their interactions and the DV after statistically controlling for one or more covariates. So it's a good example of the interface, the overlap between the ANOVA models and regression analyses and how they kind of are both part of the general linear model. So as I've already mentioned, ANCOVA is an extension of ANOVA that includes a continuous predictor variable or more than one continuous predictor variables that we want to statistically control for, and we call those predictor variables covariates. So the effects of the independent variables are assessed after statistically controlling for the covariates and partialing them out from the dependent variables and the independent variables. So ANCOVA is part of the general linear model, and as such is a special case of multiple regression where we have independent variables that are categorical and are probably the focus of our hypothesis tests, but we also have a continuous interval ratio variable or several interval ratio variables that we want to statistically control for to see what is the relationship between the IV and the DV, or what are the mean differences across the levels of the IV in the DV after partialing out the effects or the relationship between the covariate and the dependent variable. So why would you want to do that? Well, one reason is it can help you improve statistical power because, ideally, you should choose a covariate that would account for some of the unexplained variance in the dependent variable and give you more sensitivity to detect the relationship between your IVs and your DVs after you partial out the covariate. It's also used to improve the strength of a statistical argument by showing that the effect of an IV on a DV still holds after statistically controlling for the covariate. So if the covariate is an alternative explanation, let's say someone puts it forward as a confound in the IV-DV relationship, statistically controlling for it and then showing that the IV still affects the DV, still accounts for mean differences in the DV after controlling for the covariate, that can improve the strength of one statistical argument. So the null hypotheses in ANCOVA are very similar to the null hypotheses in ANOVA, that being that there are no differences between the means, or if we're talking about interactions, that there is no statistical interaction between the IVs in predicting the DV. The only difference is that now, instead of talking about the observed means, we're talking about adjusted means. So what does that mean by adjusted means? Basically, the effects of the IVs on the DV are assessed by holding the covariates constant at their mean. So that is to say, to treat each subject as if they scored at the mean level for the covariate. So the covariates, the statistical control variables, are the variables that we're holding constant to see if the adjusted levels of the dV are different across the levels of the independent variables. Right? So just as in an ANOVA, we can have main effects, we can have interactions, but instead of looking at those main effects and interactions on the actual observed means, we're looking at the main effects and interactions on the adjusted means. All right. So here we have an ideal situation where our covariate is accounting for some variance in the dependent variable, some unaccounted for variance in the dependent variable, and our independent variable is accounting for variance in the dependent variable, meaning that there's some differences between the means across the levels of the independent variable. So this is kind of a visual depiction of an ideal situation where the covariate is accounting for some of the error term and is giving us a better ability to detect the IV-DV relationship. And here's a less than ideal situation, a situation where it doesn't really even make sense to include the covariate in the model, is when the covariate is not related to the dV. So when the covariate is not related to the dV, including it in the analysis does very little to help and actually gives you less power to detect the IV-dV relationship in the sense that it eats up 1 degree of freedom for you to be able to detect the IV-dV relationship. So in this situation, unless you had like a strong beforehand prediction for needing to include the covariate, it wouldn't make a lot of sense to include it in this analysis. And then here we have a situation where the covariate overlaps with the IV and the dV. Now, ideally, the covariate overlaps with only the dV and not the IV. But in reality, it's likely to have some overlap with both. So here, it's correcting for both the effect variance, so the IV-dV relationship, and the error variance. And it's less than ideal, but hopefully if you're expecting an effect between your IV and your dV, and you've controlled for a relevant covariate and the IV-dV relationship still holds, then you have probably a more conservative test of that relationship and a stronger statistical argument to claim that that relationship exists. Right. Now, here are some rather large formulas that I've clipped out of Tabachnik and Fidel's multivariate statistics textbook. And you can watch another video of mine if you're interested in trudging your way through these formulas. But in a nutshell, what's going on here is in a ANOVA, we partition the variance into between groups and within groups. So between groups would be the effect variance, and within groups would be the error variance. But in ANCOVA, it gets a bit more complicated because we have to partition here this would be the between and within for our dV, y, and then we could partition between and within for the covariate x, and then we also have to create between and within for the cross products so that we can control for the relationship between the two. And we use these various sums of squares and cross products to create corrected sums of squares. So we could get it in a one-way ANCOVA. We'd have a corrected term for sums of squares between or effect, and a corrected term for sums of squares within or error. And we would use those corrected terms to conduct the actual analysis. And here's what the results of a pretty straightforward ANCOVA might look like. You would have a table which would give you the test for the covariates. So you'd want to see, okay, is the covariate significant? Is the covariate related to the dependent variable? And then you would have a test for your independent variable. Does that predict the adjusted differences in the means of the dependent variable? So you can assess the F and P values for that. And we also, for the first time, need to pay more careful attention to what type of sums of squares we used, and we'll get to that in a minute. But most, but not all, sources recommend using type 1 sums of squares for doing an ANCOVA, although that tends not to be the default in some programs like SPSS. So we'll get to that in a minute. And then we have the means, and these are the adjusted means. So these aren't the observed means. You probably want to look at both the observed and the adjusted, but in this output here, I've just asked for the adjusted mean. So this is a hypothetical mean if the groups for the IV had all scored the same value at the mean of the covariate. So these are the means that we're actually testing the difference for. Now, if you were writing up your results, you'd probably want to have a table that included both the adjusted means and then also the observed means. In many cases, they'll be fairly similar. You also hope that their relative rank is similar. So if you see a huge discrepancy between the rank of the means that are adjusted versus the rank of the means as they would ordinarily be observed, then that might be, a warning sign that your analysis may not replicate or may not be the best. So to assess the adjusted group means, how they come about anyway, or how they're computed, is you basically have the observed mean for each group. So that's y with the bar over it. That's the observed mean for each group. And then plus a regression coefficient. So the regression coefficient is an unstandardized regression coefficient that represents for each unit change in a predictor how many units the outcome will change. And here the outcome is the adjusted mean. And then that unstandardized regression coefficient is multiplied by the difference between the grand mean on the covariate. So here x represents the covariate's grand mean minus the group mean for the covariate. So we take grand mean minus the group mean for the covariate, multiply it by the regression coefficient, and then that is the correction factor for that group, and we add it to the observed group mean, and then we have the adjusted or corrected group mean. So that's how the adjusted group means come to exist. All right, we should briefly discuss sums of squares or sum of squares. So most books on the topic of ANCOVA will recommend that you use a type 1 sum of squares to assess effects. Now, type 1 sum of squares is basically entering the variables in a sequential order. So it makes a lot of sense to assess the covariate, the relationship between the covariate and the DV first, right? And then to assess the relationship between a main effect and the dv, and if there's another variable, the second main effect and the dv, and then if there's a two-way interaction, the interaction and the dv in a sequential or hierarchical way. So you can think of this as being extremely similar to sequential or hierarchical regression, where we have some variables that we want to look at first, and then we have the next step where we're looking at another group of variables. Here in type 1 sum of squares, it basically looks at one variable and then looks at hierarchically how much each variable that's specified next will account for above and beyond the previous variables. Makes sense to do ANCOVA this way because you usually want to control for your covariate or covariates first, and then look at the effects of your independent variables above and beyond the covariates. Most ANOVA analyses are done using type 3 sum of squares, which basically assess each effect or variable after controlling for every other effect or variable in the model. So looking at the covariate this way probably doesn't make sense, because you would be looking at the effect of the covariate on the dv, or I should say the relationship between the covariate on the dv after controlling for all of your independent variables. Makes more sense to use in the context of ANCOVA. It makes more sense to use type 1 because you want to let the covariate take its bite out of the dependent variable's variance first before you assess the other variables. So for ANCOVA, it's usually wise to use type 1 sum of squares instead of type 3 sum of squares. So ANCOVA has the same assumptions as ANOVA, and I'm not going to go over those in this video, but you can go back to the ANOVA lecture to review those. But we should discuss two new assumptions that come about in an ANCOVA, and one is that the covariate is not influenced by the treatment or the independent variable. So assuming that the independent variable is an experimental manipulation, it should not influence the covariate. And the best way to make sure that that is true is to assess the covariate prior to the manipulation of the independent variable. If the covariate is assessed after the manipulation of the independent variable, you may be on shaky ground with the assumption that these variables are independent of each other. And if they aren't, if the independent variable influences the covariate, it's probably not good for you in a statistical sense to control for it in the analysis. It's probably better regarded as an outcome variable than as a covariate. Although there's some exceptions to that. So if you're doing a ANOVA and you're doing a step-down analysis to assess the relationship between the IV and the DVs, then using one of the DVs as a covariate might logically make sense in that specific context. But usually you want your covariate to not be influenced by your independent variable. And another assumption is the homogeneity of regression slopes. So what that basically means is that you don't have an interaction between your independent variable and your covariate in predicting the outcome. So you want a similar relationship between the covariate and the DV across all the conditions in the design. So on the left here we see an ideal situation where the relationship between the covariate and the DV is the slope. The relationship is the same across these three groups. And then on the right hand side here we see that we have a problem because there is at least one condition where the relationship between the covariate and the DV is dissimilar from the other groups. So how to test that is you can look at plots, so you can create some scatter plots and fit lines by group or by condition to see if the relationships are reasonably similar, or you can uh, conduct a more formal test of the interaction between the covariate and the independent variable. So I thank you for listening to that lecture. I hope you enjoyed it as much as I did. Don't forget to like and subscribe and buy all my merch.